Good afternoon, children. Welcome to your chemistry online class. Today, we are going to discuss about a new term called free expansion. We can define free expansion as the expansion of a gas in vacuum is called free expansion. That is, if a gas expanded in vacuum, that is, pressure exerted will be zero. We know in vacuum there won't be any air to exert pressure. Such type is known as free expansion. If any expansion occurs without the presence of air or without the application of pressure, such case is called vacuum free expansion. So no work is done. That is, we are not exerting any pressure. So no work is done during the free expansion of an ideal gas, whether the process is reversible or irreversible. We are not exerting any pressure. That is, no work done. No work is done. So work done will be zero here. So work done equal to zero in free expansion. We know that W equal to minus Px by the equation. So if we have delta V substituted in equation of area of the piston that we have seen, we know delta U is equal to Q plus W. So instead of W we can put delta Px delta V. But this term, we know no work done is done on the system, so this term will be 0. So therefore delta U is equal to QV. QV denotes that heat is supplied at a constant volume. So only heat is supplying for the internal energy. So the free expansion, only heat supply will occurs. No work done. Such cases are known as free expansion. We'll see what is isothermal and free expansion of an ideal gas. We know for isothermal cases, isothermal is T is equal to constant. So for isothermal expansion of an ideal gas into vacuum, we know work done is 0. So since Pex equal to 0, also Joule determined experimentally that Q equal to 0 because isothermal means Q will be 0. Therefore, delta U, that is our change in internal energy, also 0 because heat and W is equal to 0. So, internal energy also will be 0. So, equation 6.1 that we have seen delta U is equal to Q plus W for the first law that we know. So, for the isothermal, irreversible and reversible changes, what will our equation? For isothermal irreversible changes, Q is equal to minus W, that is Pex Vf minus Vi. So for a reversible process, we have seen Q is equal to minus W, that is minus nRT log Vf by Vi, that we have expanded 2.303 nRT log Vf by Vi. This will be the equation. For adiabatic change, when Q is equal to 0, delta U is equal to WAD, adiabatic. Enthalpy. We'll see another term, enthalpy. What do we mean by enthalpy? Enthalpy is also known as heat content. It's also known as heat content. We know that the heat absorbed at constant volumes equal to the change in internal energy. If it is in the case of heat absorbed at a constant volume, only the internal energy will be given to QV, that is heat absorbed in the constant volume, that we can denote it by the letter QV. But most of chemical reactions are carried out not at constant volume. So if we check the reactions, it will not carry, most of the cases there won't be constant volume, the volume will be vary. But in flasks or test tubes under constant atmospheric pressure, this will occur. So we can write this delta U is equal to QP minus PWV. P delta V at constant pressure, that is QP denoting the constant pressure, where QP is heat absorbed by the system. At constant pressure, heat absorbed by the system denoted by the letter QP, and minus P delta V represent expansion work done by the system. So there won't be constant volume. So we have to consider it in the term of pressure. So QP minus P delta V. So we can rewrite the above equation as U2 minus U1, that is change in internal energy, QP minus P V2 minus V1, that is delta V, delta U, we know delta U is equal to U2 minus U1, change in internal energy. And delta V is change in volume. So we can rewrite the equation like this. So on rearranging the equation, we can write it as QP is, if we are rearranging, QP will come here, U2 plus PV2 minus U1 plus PV1. If we rearrange, we will get this form. Now we can define another thermodynamic function, the enthalpy. This H is known as enthalpy. Greek word enthalpine, to warm or heat content. It is also known as heat content. As H is equal to U plus PV. We know U2 minus U1 is equal to U. PV2 and PV1 we can generally write as PV. So heat is equal to internal energy and pressure into volume. So the equation becomes QP is equal to, instead of this U plus PV, we can put H. Same. So H2 minus H1, that is delta H. So although Q is a path dependent function, we know heat is path dependent function. So H is the state function because depends on U, P and V, all of which are state function. Heat is a state function. Therefore, delta H is independent of path. Hence, Qp is also independent of path. For finite changes at constant pressure, delta H can be represented in the terms delta U plus delta PV. Since P is constant, we can write delta H is equal to delta U plus P delta. Delta H is negative for exothermic reaction and delta H is positive for endothermic reaction, which absorb heat from surroundings. We know what are exothermic and endothermic reaction. If heat evolved during the reaction, that is known as exothermic. For such a reaction, delta H is negative. Endothermic is heat absorbing reaction. Such cases, delta H will be positive. And at constant volume, delta H is equal to delta U, because this term delta V will be 0. So this term will be neutralized. So we will get delta H is equal to delta U. We know delta U is equal to QV. Now we know that PV is equal to nRT. Therefore, let Na be the total number of moles of reactants and let N be the total number of moles of products. Then PV is equal to N. We know PV is equal to nRT. So PVA is equal to nRT. PVB is equal to nBRT. Thus combining both, we will get the equation like this. So we can write it as P delta V is equal to delta nGRT. And we will see what are extensive and intensive property. An extensive property is a property whose value depends on quantity or size of matter present in the system. Example, mass, volume, internal energy, etc. Extensive properties, that value depends on the quantity or size of matter present in the system. An intensive property is a property whose value does not depend upon temperature, density, pressure, etc. A molar property is the value of an extensive property, chi, the system 1 mole of substance. If n is the amount of matter, then xm is equal to x by n is independent of the amount of matter. And we'll see another thing, heat capacity. We measure heat capacity by the measurement of transfer of heat. The increase of temperature is proportional to the heat transfer. Therefore, Q is equal to coefficient of into delta T. The magnitude of the coefficient depends on the size, composition and nature of the system. We can So write the equation Q is equal to C delta T, where C coefficient can be written the letter C, that means heat capacity. When C is large, the amount of heat given out the result in a very small rise in temperature. C is directly proportional to the amount of substance. The molar heat capacity of a substance, that is Cm is equal to C by N, is the heat capacity for 1 mole of substance and is quantity of heat needed to raise the temperature of the 1 mole by 1 degree Celsius. So the specific heat capacity of substance is equal to C delta T. It remains constant. We'll see the relationship between Cp and Cv for an ideal gas in the next class. Thank you.